Okay, a little bit more about continuous monitoring now. There are a couple laboratory techniques that we can use for continuous monitoring. Probably the most prevalent one that you would see is spectrophotometry. This measures the amount of light of a particular wavelength absorbed by one component over time. So if a reactant absorbs light in the visible spectrum, or even in another specific, the UV or infrared, things like that. Usually spectrophotometry is used for the visible spectrum. Then what we can do is stick our sample in a spectrophotometer, like this guy right here, and watch as a reactant, which absorbs light, diminishes, right? Or on the other hand, if a product absorbs a specific wavelength, we can measure the increase of the product over time, things like that. Sampling the reaction mixture at specific times, if we wanted to do that, this is what we call taking aliquots, taking specific samples. So you have your reaction mixture going, and at specific times, like half hour, 1 hour, 2 hours, you can actually take out a portion of your sample and run it on some sort of quantitative analysis. You can do titrations if we're talking about slower reactions, or gas chromatography is another type of separation technique. If you know you have multiple portions of the sample, multiple reactants, multiple products, and you want to separate those at a specific aliquot or a specific given point of time, you can use a separation technique, which is called chromatography. What we want to start thinking about now is the initial rate law method. So finding the rate law. A rate law must be determined experimentally. So just like we needed data to find our instantaneous and our average rates, the same goes for the initial rate method, okay? So finding the rate law. The rate law will show how the reaction depends on the concentration of the reactants over time, and the changing initial concentration of a reactant will therefore affect the initial rate of the reaction. So we are going to be measuring the initial rates by and comparing those initial rates in order to find out the dependency on concentration, because we know as we increase the concentration of a reactant, typically the reaction goes faster. But the magnitude at which it goes faster or slower is going to be able to help us find the actual rate law. Rate laws are written as this: rate is equal to a constant K times a concentration of reactant to the power of N. And that power of N is the ability for us to say how much, what is the proportionality. The rate of the reaction is directly proportional to the concentration of each reactant raised to a power. And so that's where we're going to be able to say for any given reaction that has some reactants here, which we're going to call A and B, the rate law can be written. Now notice A and B here are not M and N over in the rate law. You may not use the reaction, the balanced chemical equation to construct the rate law. N and M are called the orders of each reactant, and they have to be determined experimentally. There's only one occasion when we actually can use that balanced equation to construct the rate expression for the rate law, and that is when we will discuss that when we get into mechanisms in just a few days. K is also important. K is the rate constant, okay? And so that rate constant is specific to a reaction. Let's talk about first the reaction order. The exponent on each reactant is in the rate law is called the order with respect to that reactant. The sum of the exponents, if you have multiple reactants, the sum is called the overall order of the reaction. So let's just take an example. The rate of the reaction here, 2 NO gases plus oxygen gas yield 2 NO2 gases. The rate was experimentally determined to be rate equals K NO squared O to the O2 to the first power. So the reaction is second order with respect to NO. And first order, imagine a little 1 up there, with respect to oxygen. Overall, 2 plus 1 is third order. Yes, this rate expression, the rate law, follows the balanced equation. This is not always the case. This just happens to be for this specific one. All right. You can have a 0 order reaction. If a reaction is 0 order, that means that the rate of the reaction does not change when the reactant is affected. Things like doubling the concentration of a reactant that is 0 order will have no effect on the overall reaction rate. The rate is actually just equal to K, the reaction constant. The rate constant units are in meters per second, and therefore the rate is also in meters per second. Rate will always be meters per second. K can change based off of the order of the reaction. First order reactions, when that superscript is 1, the rate is directly proportional to the reactant concentration. Doubling the concentration of the reactant will double the rate of the reaction. So what we see for first order reactions, when there is a superscript of 1, the rate can be written with the 1 or without the 1, it doesn't matter. Again, the rate units have to be molarity per second. Then the rate constant would be the per second, because again, if the constant K is 1 over seconds and our concentration is molarity, that's how we get molarity per second for the actual rate units. Second order, we will also talk about. Second order reactions are when the rate is directly proportional to the square of the reactant concentration. So doubling A would quadruple the rate of the reaction because we have a squared concentration there. Okay, 2 squared would be 4. Now, again, for this, if the rate is meters per second, or molarities per second, the rate constant would be per molarity per second. Let's look at this. 1 over molarity seconds times molarity squared, right? Second order. One of the molarities will cancel and we're left with molarity per second for our units of rate, which we always have to be. Now, determining the rate law when there are multiple reactants, you have to change one concentration at a time, okay? So by changing the initial concentration of one reactant, you can see how the effect of the reaction rate changes, and then keep that one constant and change the other one. So we're gonna then be examining the results based off of the differences in the reaction rate, comparing only one reactant at a time. Makes life a lot easier.